not for the balance law. And then we have these fluxes, which are based on Riemann solvers and so on. And if you want to get high order accuracy, we have a variety of non-oscillatory constructions, or we can use the discontinuous Galerkin method. And for time stepping, we can, among other things, use stability preserving Rumikuta methods, many other methods that are available. So in other words, there is a modularized, very mature numerical methods, at least, if not numerical analysis for these problems. However, there are many sort of, let's say, and the first point is that these are very, very successful. I always like to show some of these plots here. So this is a supernova simulation done in my group, 3-dimensional MHD. This is a cloud patch over the Pacific, which has been simulated with 3-dimensional Euler equations, traditional applications of flows past airfoils and so on. However, I argue that there are many intractable problems, many challenging problems, not just in numerical analysis. Many of you have heard me speak about that, but today I'll focus more on the computational aspects of it. There are many, let's say, intractable problems. And one such problem is the problem of uncertainty quantification, for instance. So what is uncertainty quantification? You're not interested in just one solution, one realization of the flow or one solution. So these are the solutions of the compressible Euler equations in 3D, some sort of a jet flow here. And this is a single realization, but you can see that this is fully turbulent, chaotic flow. So one single sample doesn't cut any ice with anyone. So you have to do statistics. So you have to do like mean, variance, histograms, PDFs, and whatnot. So that's uncertainty quantification, where the interest is in statistics instead of single realizations of the solution field, right? Now, if you want to do statistics, just for a single realization, that's why I like to put these numbers. So for a single realization, my PhD students and I, we have worked for many years to develop some sort of an optimal code. It's called ALSFIN. And we have access to one of the most powerful machines in the world, actually one of the most powerful ones in Europe, Lugano, just across the Alps from Italy. It's 12th in the top 500. And for a single run at 1024 cubed, this is the visualization of that for the density field here. This took 280 node hours. Okay, it doesn't matter. This is a unit that we use, 280 node hours. But the interesting thing is that a single run doesn't give me the statistics, right? So to give me the statistics, I have to do 500 runs or 1,000 runs. And then I can actually cost it, because this being Switzerland, I can put a price tag on everything. And if I do such an ensemble simulation, a single simulation will cost me something like $700,000 for 500 simulations. If I have 1,000, it would be 1.4 million for a single simulation. That's very, very expensive. That's what this outfit CSCS pays for these kind of simulations. So you can imagine that the computational cost becomes prohibitively large. But you don't have to go to these large scale problems to see this issue, right? So this is uncertainty quantification. Let me give you another example. And this example comes from optimal design. Many of our problems in engineering are design problems. And this is a very classical problem with compressible flows, right? So you have an airfoil, and what you can do is you can change the shape of the airfoil in order to get some good aerodynamical properties. For instance, you want to reduce the drag, keeping the lift constant, or increase the lift to drag ratio. Some let's say functionals or some cost functions. And what you do is you parameterize the shape. There's a very traditional parameterization using something called the Higgs-Henne functions. Then you solve the flow with Euler equations and Navier-Stokes equations, and you use some standard optimization procedure in order to devise what is the best shape in this context. However, even in 2D, this can be very expensive. So each simulation takes approximately 30 minutes, roughly speaking, 30 minutes of compute time. But you have to do it hundreds of times, so 500 times. And then already in 2D, this becomes expensive. And in 3D, this becomes prohibitively expensive. And why are these problems getting expensive? It's because even for a single simulation in 3D, may not be in 2D, but certainly in 3D, it's expensive, right? But the point is we have to do it repeatedly, again and again and again. And these are what are called many query problems. So you have to query the PDE solver again and again and again. And this becomes very expensive. And in fact, it's a big bottleneck in sort of full-scale use of computing and modeling in engineering applications. So this is exactly the place where we are going to take recourse to neural networks. So remember, so this many query problems, whether it's uncertainty quantification or optimal design, PDE constraint optimization, I can rewrite them in this parametric form. Okay, what is the meaning of that? So now my solution field, this could be a vector, is of course a function of time and space. In addition, all these variables, there's variables representing uncertainty, variables representing design. These are hard-coded, or they are put into one bracket, parameter y, which belongs to some finite dimensional but high dimensional space. For instance, here, this simulation is done with 20 shape functions, so 20 dimensions, and this is done with approximately 50 dimensions. So you have 50 uncertain parameters in the mix here. So let's say 20, 50, 100, these are 10, these are typical numbers that you get. And then the equations are still the same. They hold for every parameter y. So it's an additional parameter. This could be in the initial data, could be in the flux function, and so on. And the point again is that you need large number of evaluations, either with respect to the full solution field, or in many cases, for instance, the flow past airfoils, you don't care about the whole solution field. All that you care about are observables, functionals of the solution, like lift and drag. But the point is, for different values of the parameter, we have to call the solver repeatedly. So this means that this is why it is going to be expensive. So now what we're going to do is we want to reduce the cost by an order of magnitude, 2 orders of magnitude, 3 orders of magnitude, as much as possible. And we will do it by using this very interesting technique or very interesting class of objects called deep neural networks. So objective here in all of my talk today would be to approximate the solution fields for this parametric conservation law or parametric balance law with deep neural networks or observables with deep neural networks. So this would be the main objective. So what are deep neural networks? First of all, we all know, we read about it in newspapers, we watch programs about it. So deep learning is a very, very powerful tool, everything from translation to facial recognition to sort of scene identification in self-driving cars to protein folding. Many, many problems are rendered, which were considered to be impossible, are rendered possible by using deep learning or the use of deep neural networks. So to a mathematical audience, what are deep neural networks? So they're simply functions. For me, they're simply functions. They're functions which take as an input a vector, y, which belongs to some high dimensional space potentially. Remember, the space of parameters is a high dimensional space. So it takes values from high dimensional space and they produce an answer, another vector or a scalar, which might belong to a high dimensional space or a low dimensional space. So it's just a mapping, a function, mapping one potentially high dimensional space into another space, okay? Finite dimensional mapping, but it has a very specific structure to this mapping. And the structure to this mapping is compositional. So what I'm going to do is that I'm going to repeatedly compose, iteratively compose very elementary functions. And these elementary functions, so each of these compositions is what is called as a layer, because you stack things together, you keep on composing. Each of them is what is called a layer. And each layer has very simple elementary functions, which is, these are either affine functions, okay? These are either affine functions, which have a weight matrix here, a matrix and a vector, which is also called the bias vector, some nomenclature which is not important. And the result of this affine function is plugged into a scalar nonlinearity, just a very simple scalar nonlinearity, which is applied component-wise. So affine, nonlinear, scalar nonlinear, affine, scalar nonlinear, and you do it 5 times, 10 times, 15 times. I think the biggest networks have 25 times or 50 times this construction, okay? And what are the free parameters of this? The free parameters are the weight matrices, right? Because each layer has different weight matrices and the bias vectors. So I club them together into a single parameter vector or a parameter matrix, which I call as theta. And then the idea is, if you want to learn or approximate a given function, for instance, if you want to learn the lift and the drag of the airfoil, then what I'm going to do is I'm going to learn it by finding parameters which fit this function well. But what is the meaning of fitting this function? Just like we do in interpolation, I'm going to choose a set of points. The simplest is to choose them randomly in the parameter space, because this parameter space can be high dimensional. So I choose them randomly with some ambient distribution. And then at these points, I should be able to evaluate my given function, the target that I want to learn, which is often called a ground truth. So I evaluate it, for instance, by using a PDE solver or by using experimental data if I have access to experimental data. And then I look at the output of the neural network. I can just evaluate it. So they are not going to match. There's going to be a mismatch or what is called loss. And then I'm going to find the parameters which minimize this loss. Now remember, these parameters, you can remember that there are 10 layers, and in each layer there are large, the weight matrices and bias vectors of large dimensions. So in realistic problems in machine learning, the number of parameters can be in the millions or even in the billions. And this is in the parameter space, this is a non-convex function. So this is really optimizing a non-convex function in a very, very high dimensional space. So this is why it's sort of challenging. But there are algorithms to do that. In fact, the most typical algorithms are gradient descent or stochastic gradient descent, ADAM. These are different algorithms to do that. But the idea is you find some data and you train a neural network to minimize this loss function. And then that neural network should be a good approximation, or hopefully a good approximation of the target function that you're trying to learn. So very simple. The basics are very simple. Now the question is, does this work? In particular, does this work for nonlinear hyperbolic PDEs, what we're interested in? The first question is an in-principle question. So given a certain error tolerance, let's say I say my error should be 1% or 5%, can I find a deep neural network, functions of this type, of a certain number of layers, certain weight matrices, and so on? Can I find it such that this error measured in some norm, now these are functions, is going to be small? And the answer to this is yes, because neural networks have something called the universal approximation property. What it means is as long as your target is even a measurable function, let alone a continuous function, even a measurable function, then there'll always be a neural network which will approximate it to the given precision. So these are very dense in all the function spaces that you can imagine. Even for measurable functions, these are true. So the norms, of course, depend on the application that you're looking at. So in principle, yes, anything can be learned by, so compositions are very powerful representers, and you can learn many, many things by composing functions, actually anything by composing functions. But then, of course, this is sort of an existence result. It doesn't construct or doesn't tell you any attributes of this neural network. So what do? You dig a little bit deeper, look at some approximation theory with neural networks, and you have results which are of the following form. If your target function has some Sobolev regularity, then the error measured in terms of the size of the network, number of parameters, for instance, roughly scales like this. So it depends, it scales very favorably with your Sobolev regularity. If you have more regular functions, in principle, you should be able to learn them with smaller networks, and it scales badly with respect to the dimension. If you have more dimensions, then you get hit and you can't learn it that well. So now let us apply it to the concrete case of hyperbolic PDEs, right? As all of us know, our mappings, just imagine that we are trying to learn, for instance, the mapping with, let's say, the whole flow field. This is not going to be very regular. It could be BV, that's a good approximation we can make. And perhaps the observables can be Lipschitz under some assumptions. But we can't do better than that. We have to look at essentially BV or Lipschitz, something in between. And that doesn't make a huge difference because you just change the norm. So even if it's BV, and if you just have 6 dimensions, parametric dimensions, not physical dimensions, then to get 1% error, I start plugging in these numbers. 1% is 10 to the power minus 2. And 6 dimensions, you get a network of size of 1 trillion. So your network has 1 trillion parameters, and it seems almost impossible that anything useful is going to come out of it. Remember that the biggest neural networks that we have at the moment, which have very, very large dimensional data, they still have billions of dimensions, not trillions of dimensions. No one is able to train this. So the reason why we have these big systems is because we are hit by the curse of dimensionality. The size of the neural network grows exponentially in the dimension. If you just look at the fact that it's a BV function or it has some Sobolev regularity. So this is not going to suffice, and it tells us that the problem is very difficult. Thankfully, there are workarounds this, and one has to do a little bit more refined analysis. And I just presented for a very simple case because we can only prove things in a very simple case. So it turns out that this error, which is in any LP norm here, it decomposes into three pieces, something called approximation error, a generalization error, and optimization error. Let me try to explain this a little bit. So approximation error is, for those who know finite elements, just the best approximation. So you have something belonging to a Sobolev space, and you're going to project it onto a subspace. This subspace, for instance, could be the space spanned by neural networks. So, or a manifold, which is spanned by neural networks. And you ask a question about what is the best approximation that you can do. So remember that this best approximation was the one, the best approximation was the one where we had this exponential dependence on the dimension. It turns out that for multidimensional scalar conservation laws, where we can prove it, but you can do it in more generality under some reasonable assumptions, you can actually prove that this approximation error does not depend exponentially on the dimension. It depends polynomially on the dimension, and not just polynomially, with very small polynomials. So if it's parameterization only in the initial data, then it is linear in dimension. And if it is parameterization with the flux, then it's at most quadratic in dimension. So this makes it reasonable, right? Let's say 6 dimensions, even if it was quadratic, you get a factor of 36. And to get this eta is close to 1, actually. So think of it as 1. So now the parameter has only 3,600 parameters. The neural network will only have 3,600 parameters compared to 10 or 1 trillion parameters. So this is where the curse of dimensionality can be mitigated, right? And it's a very powerful. So this is good news in a way, that small neural networks can approximate solutions of conservation laws, even if you have shocks and so on. This is not a problem. But the problem here is that there are other pieces of the error. For instance, optimization error. Now, this precisely is this very high dimensional, even if it is 3,600 dimensions, it's still a very high dimensional non-convex problem. And if you ask me rigorous results on stochastic gradient or gradient descent algorithms, they're simply not available. So this is very hard to do anything theoretically in terms of the optimization error. However, what you can do is when we are training these neural networks, empirically, we know what the training error is. So this is something that we can verify a posteriori. We should try to train as well as possible so that we get reasonably low training errors. So this is something that can be monitored, even if it can't be proved with the current machinery. The final piece of error is what is called the generalization error. So this stems from a very simple observation, that my error was a norm, right? It was over the entire population or over the entire parameter space, whereas training happens over a subset, randomly chosen, but still a finite subset. So think of this as an integral, which it is, and think of this as a quadrature, which it is. So the difference between them, the error is really a quadrature error. These are random points. So you would expect something like 1 over square root of n, Monte Carlo type, central limit theorem type estimates. But it turns out that these are not independent because the training couples them. So one has to work hard and use some concentration inequalities and some standard techniques from learning theory to get that this error behaves like square root of n, but with a logarithmic correction. So logarithmic correction is not so bad. So now let's put all these three things together. We know that small neural networks can approximate solutions of conservation laws or balance laws for that matter. And the total error, I'm assuming that these errors are small because one can be monitored, the other can be made small. But still, the overall error is going to behave like 1 over square root of n. So remember this, 1 over square root of n, which is quite okay for people doing traditional machine learning, but which is a big problem for us. Why is that? So even if I'm assuming that the numerator here is order of 1, which need not be the case, let's say that it's order of 1, still to get 1% error, 10 to the power minus 2, I need 10,000 samples. Now, these are the training samples. Remember that I have to train the neural network here to find the best fit. But these 10,000 training samples have to be generated from data which comes from here, which is okay, but still it's 30 minutes. So this is 5,000 hours of compute time, which is a lot of time. And here, this is impossible. Like even to generate 100 samples is quite expensive. So you cannot. So the regime that we are working with in general, this is not a good fit. So our challenge is that we are learning maps of low regularity, right? Because that's where low regularity, but in a data poor regime, because we simply don't have the data that facial databases have, that linguistic databases have, that sort of just vision has. So we don't have that kind of traditional databases. So this is a big difference between this and sort of the big data success of machine learning. And we have to confront with this problem. So today, the next few minutes, I'll explain some attempts or some ideas on how to confront with this small data problem, relatively small data problem. So it turns out that we can do this with many tricks that we learn in numerical analysis. The first trick is, so it's true that in machine learning, most of the data is assumed to come from a randomly distributed or from a distribution. So it's randomly sampled. But our data is synthetic, right? We are computing it, we're simulating it. So there's no reason why we should acquire it in a random manner. So imagine that if even in a high dimensional space, instead of using random points, if I use better distributed points, for instance, what are called low discrepancy sequences. Now here is a picture here. So I take a low discrepancy sequence, something called Sobol sequences. And then you can see that many of these boxes here, they don't have random points. This is just 100 points, so they don't have random points, but they have these orange stars. So these are actually equidistributed or better distributed. One can make this mathematically rigorous, but just for intuition, they're better spread out in the parameter space. And in fact, they're the basis of what is called a quasi-Monte Carlo integration. So the first trick here is don't use random points, use much more structured training points. For instance, low discrepancy sequences. Then one can prove theorems, which don't always apply to conservation laws, but nevertheless, one can prove theorems. For instance, one can prove that if your target, neural networks always satisfy this hypothesis, but if your target has what is called a bounded Hardy-Krause variation, so it's a generalization of total variation, but it's not total variation. There are more terms, more mixed derivatives here. Then one can prove that your error, total error now, behaves not as 1 over square root of n, but 1 over n linearly, but with a logarithmic correction. Okay, this is a dimension-dependent logarithmic correction. Unfortunately, for conservation laws, I don't know a way to actually prove that the solutions are in this class of bounded Hardy-Krause variation. I've never been able to do that. However, if you have elliptic or parabolic PDEs, the situation is much better because forget about bounded Hardy-Krause variation. Under some reasonable hypothesis, you can prove that the map is holomorphic, it's analytic. So in that case, you can use some special structured data. And instead of having a 1 over n and with some logarithmic dependence and dimension, you just have a quadratic convergence, which is also shown in numerical experiments. And you're not constrained anymore. You overcome this curse of dimensionality. There's no dimension dependence anymore. Here, there is a mild dimension dependence. And also in numerical experiments, even though it has not been sort of proved for conservation laws that this is the case, we do see that this is indeed helping us. So this is the first trick that we are going to use. Use more structured data points. The second trick that we can use, which is also common in numerical analysis, is to use what is called multi-level or multi-fidelity training. So remember that this data that I need for my neural networks, they are from some numerical simulation. But as always, we don't have numerical simulation only on one mesh. We have it on a sequence of meshes. And this was sort of the success of the multi-level Monte Carlo methods that many of you know I have worked for a long time. And what we do now is that we use this idea. So instead of learning the map, the numerical approximation of the underlying map at this resolution, we look at it at, let's say, 3 different resolutions, coarse, finer, finest. And instead of learning the full map, we learn what are called details. So details are the differences between the resolutions. So instead of 1 neural network, we have 5 neural networks. And the point is that we can prove in this case that as long as the variance of the details, because these are convergent numerical simulations, so between 2 meshes, the difference is going to be small. As long as the variance of the details decay, then we can prove under some reasonable assumptions that the speed up of this procedure is guaranteed. And we also observe that in practice. So we can combine these 2 things. We can train with quasi-Monte Carlo, or let's say low discrepancy sequences. We can use multi-level training and we can combine them. And then we can do some realistic problems. So let me give you a few examples of that. So this is a very traditional example, just prediction. What does it mean? So I have an airfoil here. This can be done in 3D. We haven't gotten around to do it, but let's say 2D, a wing cross section. You have Euler equations. So the flow is modeled by the Euler equations with some Mach number, with some angle of attack. The shape is what is changing here. And now as a function of shape, you're going to predict either the full solution field in steady state, or you're going to predict the lift and the drag. So the point is this can be done with very few training samples, 128, that's the example. The neural networks are relatively small. They're anything between 1,000 to 10,000. Maybe the biggest ones are like 30,000. And the point is, as you can see, this is your exact density, the ground truth. And this is the prediction. And the prediction looks very good. It's close. Of course, it's slightly dissipated out, so which is also seen in the accuracy. It's about, I think it's about 1.7%. I wrote 1.9%, but it's in the, let's say, less than 2%. That's not the main point, that it's a very accurate simulation. The main point comes here. So to generate this for any new shape, I have a very optimized code, but still in 2D, it's a steady problem. It takes time. So it takes about 40 minutes. This is a number. It could be 5 minutes for some, let's say, coarse resolution. But at this resolution, it takes about 40 minutes. Now, when I evaluate the neural network, look at the amount of time it takes, 0.2 seconds. So now, as you can see, 40 minutes to 1/10 of a second. So I have a scaling which is like from a scale of about an hour to 1/10 of a second. So I have 3 to 4 orders of magnitude right there. So this can be by the time this, but of course there is some training time that neural network has to be trained, and this takes about 1 hour. So you get 3 to 4 orders of magnitude speed up in this particular problem, even with shocks and all, at reasonably high accuracy. But if you're just interested in things like the lift and the drag, these objects are relatively better behaved than the whole flow field. Still, you can do it again to very high accuracy, 1 to 2%. But now you can do it. This still took 40 minutes, right? If you give me a new shape, I don't know the lift and the drag. I need to predict it from a simulation. Whereas from the neural network, it takes me 10 to the power minus 5 seconds. But it's just one number that I need to tell you, right? So this was again 10 to the power 4 seconds or 10 to the power 3 seconds. So right here, you have 7 to 8 orders of magnitude, right? Because now you're just asking for a number. So this makes it very, very quick. And the training time is also very quick. So you are able to, with a few samples, small networks, get high accuracy at a fraction of the cost. And this is the whole point about this sort of surrogate modeling. The second example is now once we have these surrogates, which are well-trained, what we can do is we can apply them in different problems, right? So here's uncertainty quantification, which can be paraphrased as finding probability distributions. So here, for instance, is the same flow field with different perturbations of the shape. And now we are predicting the lift and the drag. And as you can see, the surrogate is simply, instead of using Monte Carlo or quasi-Monte Carlo with my exact solver, I've simply replaced it with the surrogate. So I've trained the surrogate and then I just use that. And as you can see, visually, they are very close to each other, very accurate computations. And when you do now, of course, it's uncertainty quantification. So you have to add the training time, which is the time for generating the samples. And still, even with that, over Monte Carlo, it's 2 orders of magnitude speed up. And with quasi Monte Carlo, which is really state of the art for these kind of problems, it's still an order of magnitude speed up. And if I would have used multi-level training, which I don't show here, it's another factor of 3 to 5. So you get around 30 to 50 speed up, which for uncertainty quantification is considerable. So this is one example. Another example that you can use it is PDE constraint optimization. Remember this problem of designing airfoils such that the lift is held constant and the drag is minimized. So here, of course, you have a solution of the PDE, let's say with respect to an observable, you have some cost function and you have to minimize this objective function in parameter space. Now, of course, the simplest thing would be to replace this function with the neural network surrogate. But that doesn't work so well, even though it's very cheap to evaluate, it doesn't work so well because the basic idea behind neural networks is somehow you have to learn things, information on the whole parameter space. However, your optimizers are not spread out randomly in your parameter space, right? They are probably sitting on some manifold or sub-manifold or some other structure on a low-dimensional, potentially even a low-dimensional set. In this case, it's just a manifold here, a curve, just to visualize. So your optimizers are on this curve. Now you're trying to learn the solution everywhere, right? So unless until you have a lot of points, you will miss this manifold. So the solution that worked very well is to do what is called active learning in machine learning, but which is to choose the training set iteratively. Let me explain that. So you start with a few points, 16 points or 32 points. You train a neural network. It will not be a very accurate one, right? Because it's taking a very few points. Nevertheless, you run your optimization algorithm. This takes the speed of light because the neural network is very cheap to evaluate. And this gives you a new set of optimizers, that you use as your training points. And then you iterate the process. So you first train, optimize on the surrogate, then use the optimizers as the training points, train, optimize on the surrogate, keep on doing this. So you get some sort of exponential benefit from this iteration. And under some idealized conditions, one can actually prove that this is exponential. But nevertheless, in real life, these idealized conditions are not met, or convexity in particular. Nevertheless, let me give you a realistic example. So this is with these 20 shape parameters. You have this shape function. And now you can see that I started with some reference shape of the airfoil. And I could reduce the drag to 50%, which is what is not unexpected here, by slight changes in the shape through this optimization procedure. This can also be done by a traditional algorithm, some Newton algorithm. But the point is that will require 2,000 evaluations, forward solves. To get the same level with the machine learning algorithm, it takes me about 60. 60 forward solves. So this is where the cost lies. So I'm able to benefit a factor of 30. So on optimization problems and 3D, we believe that the speed up will be much, much more because 3D problems are even harder to solve. But already in this 2D problem, we were able to come up with this, right? So this is the first, this is another example of this. Now, my final example, which we are still working on. So I wanted to present this because many of you are Italians or sitting in Italy. And this is a joint collaboration with some people at INGV and people at Malaga, my old pals from there. And the idea is to simulate tsunamis, earthquake-generated tsunamis in the Mediterranean. I think many of you know that I've been working on this for a while. And today, the best way we do it, of course, we solve the shallow water equations, two-dimensional balance laws. And the main difficulty is that when an earthquake happens, the seafloor deforms, and you have to convert this seafloor deformation into initial conditions for your shallow water waves, right? And this is done by something called Okada model, which has about 9 to 11 parameters, depending on which flavor you do. So at the moment, even with a very optimized code, which is developed by people at Malaga, the uncertainty quantification and prediction takes about 60 minutes, which is a big achievement. This used to be days before, right? Still 60 minutes is a big achievement. Nevertheless, 60 minutes is too long for these applications, right? So now we have not finished the project, but the initial results are very, very good. So I'm just highlighting the Italian coast, and we want to learn the time series at specific points. So let me go to the worst prediction in our model. Again, the same ideas have been used. It is somewhere in Calabria, and you can see that this is a very complex time series in this case, waves coming in, big waves, small waves, and so on. And even the worst prediction does a very good job. It's about 1% error. So on an average, we do less than 1% error. And again, it's a fraction of a second compared to 60 minutes. So again, you get the same sort of 3-4 orders of magnitude scaling. So yes, so this is a very successful, at least at this level of problems, is a very successful method. I hope I've convinced you. But now for the remaining 10 minutes of my talk, I will just try to highlight some of the deficiencies of this approach and tell you about new possibilities in this direction, right? So remember that whatever I showed you with the surrogate modeling and with speedups and so on, this required, first of all, I needed to know the PDE. I needed to know its Euler equations or its shallow water equations and so on. I needed to know a good parameterization. This was the key, right? So this Okada parameterization has been developed for 50 years in this seismic earthquake community. Similarly, the Higgs-Henne functions for the airfoil have been developed for the last, God knows how many, 30, 40 years. So you need good parameterizations, which how do you do these parameterizations? Okay, in design, you know what the parameters are. Otherwise, you're supposed to know your measure. You know, there is a measure from which everything is happening. And if you know the measure, then you can parameterize it. For instance, by the principal component analysis or Karman and Love expansion or something like that. And the final ingredient is that you needed a numerical discretization because that's where the data came in. And these three ingredients worked in these problems, right? Because we had access to them. But in reality, what we have is that who knows, okay, some of these problems, the physics is classical, but many problems, the physics is either incomplete or is missing. So you don't have PDEs that describe it completely, which can be a problem, might not be a problem, but I would say that it's a serious problem. The data is not from numerical simulations. It comes from experiments or observations in many cases. And then the difficulty is that we don't know the underlying measure. Since we don't know the underlying measure, all that we can do is to do empirical stuff from it. We can sample from it. But if you have only 100 samples, then you really can't build parameterizations with 100 samples. The sampling error is going to be like 10%, and it's square root of the number of samples. So it will be 10% just from the sampling error. And so this is the biggest problem. So you, at least in my view, so it is difficult to design good parameterizations unless until one has worked for 50 years. The community has worked for 50 years in an area. Another thing is that you're completely constrained by your parameterization. If you have something which is very close, but it's not fitting into your parameterized sort of manifold, then you can't even predict what's going on. Final issue is that since we're using numerical simulations, there is you only learn the numerical approximation. At a different numerical approximation, you might do badly. So all these issues, and particularly the lack of good parameterizations, this necessitates what is called operator learning, because in principle, in PDEs, you shouldn't be learning maps, you should be learning operators. So what is operator learning? And I'll just give you a very brief introduction and I'll stop after that. So the basic thing is that we have been given an abstract PDE. Just imagine conservation laws, right? And the input to the PDE is initial data. So a PDE, what it does, solution operator of a PDE is that it takes a function, initial data, could belong to PV, for instance, and it churns out another function, which could be the action of the solution operator at time t. So in all PDEs, you can identify that what is underlying the input-output response in a PDE is actually an operator, a mapping between a function space and another function space, right? So to build a surrogate, we don't just have to learn the parameterized version of it, but in a parameter-free manner, we need to learn the entire operator. So in fact, nowadays, last 2 years, there has been an exponential growth of interest in operator learning. And what I'm going to focus on today is one recently proposed paradigm, which is called deep operator nets or DEPO nets. So what are DEPO nets? First of all, they've been around for a while. They were proposed by two Chinese computer scientists in 1995, Chen and Chen. But George Kaniadakis at Brown University, he sort of resurrected it, he improved it. And in his group, they've done lots and lots of numerical experiments to show that this is a viable framework. Let me just explain what it is very briefly. So remember that my input to output map is an operator. So given a function, I should churn out an approximation to another function, right? An operator. So what it does is the output space is a function space, right? So first it tries to find a basis for this function space. So this basis is a neural network. It's called a trunk net. So the output function is parameterized in terms or is characterized in terms of this basis function, which is called a trunk net, another neural network. And then the coefficients of this basis function are parameterized in terms of another neural network. So given an input function, what I do is I read out its values at a fixed set of points, what are called sensor points. And then I process them through a neural network, which is a mapping between a finite dimension and another finite dimension, to produce the coefficients of this. So we have a function as the input and a function of the output. And the trunk net is like a basis function of the output space. And the branch net is what provides the coefficients. So this is sort of the representation, very briefly. Now, why should this work? It has two sets of neural networks which are acting in parallel to produce output. And the reason why it works is because already in 1995, these guys, they were able to prove that there is a universal approximation theorem. So just like neural networks can sort of approximate any function, these DEPO nets, or operator networks, can approximate any continuous operator. Any continuous operator from a compact set. For simplicity, I took continuous functions, but for compact set, this is important. Two continuous functions, so they can approximate anything. Well, this is a good result, right? So there is some universality. Of course, in practice, your input space is not a compact set, right? It can be more general than a compact set. So the utility and G also can be discontinuous. But so this is one of the big issues with this theorem. But nevertheless, in principle, it is possible. And the other thing is that it's not a constructive result. It's an existence result, right? So you don't know how many of these networks do you need, what is the size of these networks, how many branch nets you need, how many trunk nets you need, how many sensor points you need. No explicit information is available on these things. In particular, the fear is, remember that with the finite dimensional problem, you had this curse of dimensionality, right? Since you had this curse of dimensionality, you had, which was exponentially growing with dimensions. Now, since you have infinite dimensions, the question is, will it also grow exponentially in a sort of an infinite manner? So could this be marred by the curse of dimensionality? And this is what set us going into this problem. So there is a very long paper from Samuel Lanthala, a PhD student of mine, and George Kaniadakis, where we proved that, first of all, we proved that the universal approximation theorem is more general. You don't have to restrict to continuous functions or compact sets. But what you need is you need a measure, because all the time you need a measure on your distribution on what you're drawing from. So you need a measure on the probability measures on function spaces. And once you have that with respect to this measure, you put your error, you define your error with respect to this measure, which is also what is done in practice. In practice, you just do a quadrature on top of that. So you don't have any compactness assumptions and you don't have any continuity assumptions. So measurability is good enough. So it's a very general approximation result. It puts you in the same class as what you had for functions. So universal approximation for functions. Of course, it doesn't solve the curse of dimensionality. So to handle the curse of dimensionality, one needs a much more refined analysis of this. This is a very long paper for that reason. And the analysis is done by the following. Instead of using this framework, it's easier to explain it in this sort of commutative diagram, let's say. So remember that my target is an operator mapping a space X to a space Y. Now this is a function space. So the first thing I do is I read out the function at a few points. I can also take local averages if the function is not continuous. And so this is an encoding step, a projection from infinite dimensions to finite dimensions. Then I pass this through finite dimensional neural network. So this is what we call approximation. And finally, you have to go back from this finite dimensional space into an infinite dimensional space. So you have to reconstruct. And this reconstruction is, or lifting, some people call it lifting, is done with respect to this trunk nets. So instead of looking at this operator, what we do is that we look at this composition. And so each component of the error can be divided into its appropriate components. So I really don't have the time because I'm running out of time. Giuseppe, can I take 2-3 more minutes? Or I forgot how much time do I have? Giuseppe?
Yes, sure. You can take 5 more minutes.
Okay, I'll try to conclude it in 5 minutes because it sort of becomes a bit technical. So the main point is that you have these 3 sources of error that one has to control. Now, cutting a long story short, the first 2 sources, no, not the first 2, the encoding error and the reconstruction error, these are essentially projections or projections from the infinite dimensional space to a finite dimensional space, linear or affine projections. So you can use essentially linear function analysis. You can work with the covariance of the covariance operator and with the eigensystem of the covariance operator, and you can control the error by using the covariance structure of the push forward measure. But maybe I don't have the time to explain the details. But these are really linear or affine, let's say, control of linear or affine approximations, which is not hard, but it still needs to be done. There's some technical difficulties. But it's the last piece of error, which is the approximation error. This is now nonlinear, and this is a mapping from a finite dimensional space to a finite dimensional space. So you could use traditional neural network approximation theory to say that the size of at least one of your neural networks has to behave like this. Remember, the regularity and the dimension. These are the 2 things. So K is the regularity, M is the dimension. Dimension now is given in terms of the projection here. So it's a number of sensor points. But this is where the catch is, because in order to reduce this error, the error at the encoding step, at the projection step, I need infinitely many components, right? So M has to go to infinity. Otherwise, it's a finite dimensional problem. And since M goes to infinity as epsilon goes to 0, so you have 1 over epsilon times something which goes to infinity as epsilon goes to 0. So you have this double exponential growth. And this means that this a priori shouldn't work, right? It's a double exponential growth. However, we are much more structured in PDEs. Forget about elliptic PDEs and let's focus on hyperbolic PDEs, scalar conservation laws for simplicity. So scalar conservation laws, no parameterization whatsoever. My operator is a mapping from U0, which is in, I think I needed it in BV. And this is a mapping from BV to BV, but we look at it as a mapping from L1 to L1. And of course, now we don't have the L2 sort of settings, but by hand, we can prove many of these results. And what we essentially do is that we are able to prove that the size of the neural network, instead of growing exponentially times an exponential, it grows polynomially in the error. And this depends, D is a physical dimension. So if you are in 3 dimensions, this is just 3. Alpha is close to 1. It's related to the rate of convergence of a Lax-Friedrich scheme. So this is the good news, that there is no curse of dimensionality for hyperbolic equations. The bad news is that since the mapping is only Lipschitz continuous, the best you can do, there is even lower bound, is 1 over the number of trunk nets. So if you have, let's say, you want to have 1% error, then you need 100 of these basis functions, which is quite a lot. So computationally, it's still heavy, but of course, you don't have any parameterization, so you have to pay the price somewhere. So we have some initial numerical results which are encouraging. It's still not at all in the same class of results that we had before, because now we have no parameterization whatsoever. In fact, the inputs here are from a Gaussian random field, a Gaussian measure, an infinite dimensional Gaussian measure. And you can see that these are typical examples of the inputs, and this is how the solution is. You have some shocks, some rarefactions, and so on. You have no information about, you just see some training samples of Gaussian random fields. and no information about the characteristic scales, about the characteristic time scales. You have to learn all of this on the fly. So you get 3 to 4% error. This can be improved with some other techniques, but it still does quite well. So even though the difficulty was already inbuilt here, that you need a lot of trunk nets, you still can somehow circumvent this difficulty. So it's sort of encouraging, and it's completely a parameter-free manner. So if you don't have parameterization, just use this. Anyway, so with this, I want to stop now and just summarize. So my main point was to link deep learning with nonlinear hyperbolic PDEs, at least the work done in my group. There are many other efforts in this direction. And in the first part of the talk, I spoke about many query problems where the models were parametric hyperbolic PDEs. And we had lots of tricks, but we could, or some standard tricks, and we could really solve this problem of learning in a data poor regime. And there were several examples that I showed you where the errors were 1 to 2%, but it was 2, 3, 5, 6 orders of gain in speed up. What I didn't talk about is Bayesian inverse problems. This is really encouraging results we already have on Bayesian inverse problems. So this was the first part of the talk when we had parameterizations. If you don't have parameterizations, you have to use operator learning. And I also indicated some of the potentialities as well as some of the challenges in doing that. But deep nets are not the only paradigm. There are many, many different paradigms these days. One is very successful. It's called Fourier neural operators. To me, it's a sort of glorified spectral viscosity method, which was proposed by people at Caltech and got a lot of attention to the community. We have extensive analysis of this also in another paper. It also breaks the curse of dimensionality. And in fact, I didn't show you this, but we have better results for the Burgers equation with Fourier neural operators. And the main point that I want to say is that many people are trying to use deep learning in the context of solutions of PDEs, but we can't do it in a black box manner. We can't just take what is available and plug it in and things will work. No. So as I try to convince you that it does require significant amount of innovation. So there is plenty of intellectual content and very interesting mathematical problems that arise as a result of this. So thank you very much for your attention, and my apologies for taking a couple of minutes extra.
Well, first of all, many thanks for the very nice lecture. Are there questions in question? Please go ahead.
I can't hear anything, nor can I see anyone.
I'm Corrado for the talk.
Hey, Corrado.
It's very interesting talk, but I was a bit lost since I was expecting something with some more PDEs, some more explicit work on PDEs, while it was slightly different, but in any case. So you are presenting many things concerning, for example, scalar constitution, hyperbolic scalar constitution, so Burgers equation. And actually, my basic question is, have you tried something in some more realistic environment concerning, for example, the cases in which you have a system and you have a physical system which has, for example, as the form of it's more or less like a shallow water equation with some viscosity in the second equation. So you have some conservation of mass, if you want, coupled with some second equation which is parabolic. So would you expect something better in terms of results that can be obtained from the parabolic part of the system that can, in some sense, partially at least counterbalance the hyperbolic nature? So what does it happen when you have something that is has this kind of mixed structure of being hyperbolic, parabolic? I don't know if I'm you.
Yeah, I got your question. There are two things here. First of all, in terms of the sort of numerical results, most of the numerical results, okay, except for the last part, I didn't present anything from Berger's equations. All these are systems, right? So this is a two-dimensional conservation law, Euler's equation. This is a two-dimensional conservation law, shallow water equations, or balance law, shallow water equations in bottom topography. So the numerical results are always in more realistic settings. Otherwise, these papers won't be accepted. But of course, the theory there means less well defined, because the theory requires much more structure. So your question was, if I have something hyperbolic and then something parabolic in the second component, can I, for instance, prove something like, let's see, a result like this, for instance? Can I prove something, a result like this? It depends if, so for instance, it depends if you have a result which says that a numerical method approximating this equation has a certain rate of convergence. Okay. If you have such a result, then yes, I can convert that kind of a result into a theorem like this. No problems with that. Because all that I need is some abstract structure, and in that abstract structure, all that I care about is there exists a convergent numerical method with a certain rate of convergence. In fact, the rate of convergence is given in terms of this eta. So yes, there are many problems where this is possible, many other problems where this is not possible. So depending on, at the moment, with the techniques that one has, this is a necessary restriction. Means that doesn't mean that there are someone else will come out with something different. But I don't need a lot of structure. All that I need is a convergent numerical method, which is reasonable. Then I can.
Thank you.
There are some things. Yeah.
Okay. I see, but why it is true that if there exists a good numerical method for which you can control the rate, why your network will be the same quality?
Yes, that's a very, very good question, right? So the answer is, well, I think Giovanni wrote in the chat that he can't hear the question. So perhaps I will try to paraphrase the question first. So for those who are not there. So the question was, what's the connection, right? If you have a good numerical method with a convergent rate, how can you sort of remember that how can you say that your neural network is going to at least have that rate? So what you do here is that, yeah. So this is, as I say, this is the best approximation, right, in the space of neural networks. So if you give me such a numerical method, I can use, let's say, a constructive manner of being able to represent that numerical method with neural networks, or being able to approximate that with respect to neural networks. So because I can represent that with at least, means, it can do much better, as it does, right? The theorem says something and it gets much better results. But at least I know that I can represent it in the class of neural networks. So the best approximation error will at most be that, right? It could be that it's much better. In fact, in practice, it should be better. But this is very difficult to prove because it's a worst case guarantee. So there is a deep connection between numerical methods and neural networks. In fact, you can think of neural networks as being sort of numerical methods with tunable coefficients. There is equivalence between them, and you can use leverage that unless until you have some special structure. If you have analyticity or some other special structure, you can leverage that to get a similar result.
More questions?
I see that Giovanni's hand is raised.
Yeah.
Okay.
May I ask a question?
Please, John.
Oh, thanks, Giuseppe. Actually, I hear very well, Sid, but I cannot hear very well the people who talk in the audience. So I don't know if this question has been already asked. You referred to the solution of a direct problem that depends on the some parameter y. And then you would use like a sophisticated or accurate numerical method to solve this problem. But of course, if you have to solve a problem many times, perhaps especially in the first stage in which what you need is a rough approximation, perhaps one could couple these techniques with the model order reduction. to obtain some tools that is much less costly, especially in the first stage, in which you need a rough approximation to identify, as you said, what is the region of the parameters where it is more likely to find a good approximation, a good solution. And then you may refine and use maybe a more sophisticated model order reduction methods, or when you're really close to the optimal solution, then you can use a sophisticated direct numerical solution. Can you spend a few words about this?
This is a very, very good idea, Giovanni, except that it has already been done by many people. So I think there are many results. In fact, this is what is called multi-fidelities. I just focused on the multi-level training.
Okay.
But one could use multi-fidelity training. There are different ways to look at it. One could use multi-fidelity training. I think several people do it. I don't want to take names because then I will leave out some people. But what they do is essentially what you say, that one could start with something rough, or one can have the difference between a rough and more fine resolution of the system, and then one can learn. And these techniques also have been proved to benefit the training for sure. So this is an important point. Regarding model order reduction, as you know, hyperbolic problems are very difficult to do model order reduction on. For elliptic or parabolic problems, you can do model order reduction, but for instance, the same problem of airfoil, this example, people can have also tried to do this with model order reduction, but they don't get the time down to 4 orders of magnitude. If they're lucky, they get it down to a factor of 10. So in fact, for elliptic and for parabolic problems, people have even, I think in Alfio Quattroni's group, Wolfgang Dahlmann, many people, they have actually shown that the traditional model order reduction techniques, they do better than neural network techniques in that setting, right? So, or at least they're no worse. But for hyperbolic problems, this is far from the case, because traditional linear model order reduction doesn't do a good job, whereas this is a nonlinear approximation, and this does a much better job. So these are exactly the sort of problems where this works very well. So I agree. So one could just use a coarse solution, right? Why use model order reduction? Because model order reduction is difficult to do for hyperbolic problems, comparatively, compared to elliptic or parabolic problems.
Okay, thank you.
More questions from people online? Okay, so I think that we can thank again Starta and all the speakers of this afternoon session.
Okay, ciao, bye-bye. I should stop.
Bye-bye.
Bye.